we must have at least some, albeit unreal, idea of what nuclear matter is. This was said for the first time by our compatriot Georgy Antonovich Gamov, a graduate of the Leningrad University. Here is his portrait. In 1928, he said that the nucleus must be very similar to a drop of liquid, to a drop of charged liquid. By that time, it was known that the nucleus has well-defined edges, a spherical shape, and is incomprehensible. And this idea of his, in fact, is very bold. And I would say very strange that one can apply the idea of a macroscopic body, a drop of liquid, to a micro-object, which is the nucleus of an atom. Nevertheless, the idea turned out to be very valuable. It allowed Gamov to create a theory of alpha decay. We will talk about that now. But the idea also allowed Weizsäcker to create his famous formula for the binding energy inside the nucleus, and Bohr and Wheeler to create the theory of fission, while alpha decay, as discovered by Henry Becquerel in the 19th century, is that the nucleus can spontaneously eject another nucleus from itself, a helium nucleus, an alpha particle, only if the condition is satisfied that the mass of the parent nucleus exceeds the sum of the mass of the daughter nucleus and the ejected helium nucleus. This, however, is hindered by the large Coulomb barrier, because the helium nucleus is charged, and in order for it to leave the mother nucleus, it must pass this barrier. This requires a lot of energy, and it would seem that this is impossible, because the energy of the alpha particles is approximately 6 to 7 megaelectron volt, while the height of the Coulomb barrier is 30 to 35 megaelectron volt. However, this is where quantum mechanics gets entangled. And Gamov proved that, for example, if you play tennis and hit the ball against the wall, the ball rebounds. You hit it again, it rebounds again. You hit it 1,000,000 times, it rebounds each time. You hit 1,000,000,000 times, it still rebounds. This is classic Newtonian mechanics. If this whole process is taking place in the microcosm, and the ball is a particle, then, generally speaking, with a certain probability, it may end up behind the wall. It seems to tunnel through this wall. Somehow, it seeps through this wall because, in quantum mechanics, there are no trajectories. There are probabilities of finding a given particle at a given time, at a given point in space. And this penetration is purely quantum mechanical effect, and shows that any barrier can be penetrated. The only question is the probability of this permeability. Gamov wrote a permeability factor in the following form. He first considered the number of attempts made to penetrate the barrier, which is very large, about 10 to the power of 21 per second. Gamov looked at the probability of penetrating this barrier for each attempt, and from there calculated the transmission coefficient, which is exponential to the minus 2g power, where g is the Gamov factor. And for this g, he wrote a formula, which in its pure form includes the profile of the Coulomb barrier and the energy of an alpha particle and a certain inertial parameter and mass, which allows him to calculate the probability of this decay from the lightest nuclei to the heaviest. Here is an example. The radium-226 nucleus has a 50% probability of emitting alpha particles with an energy of 7.84 megaelectron volt over a period of 1,600 years. This graph is in fact easily understandable if you illustrate the nuclear potential, then you illustrate the Coulomb potential, and add them up. Then you get this barrier, the so-called barrier through which the alpha particle needs to penetrate. And as a result, it will change from nucleus to nucleus. The probability of this penetration is thus how Z changes by the root of the alpha particle energy. This is the famous expression of Geiger and Natal, proposed back in 1911. It works great for all nuclei, from the longest to the shortest lived. I have to say that this does not only apply to the alpha particle. Generally speaking, it may not be an alpha particle, but some heavier formation, for example carbon, neon, for example magnesium. The radioactivity of carbon was observed in England, and heavier formations of elements such as neon, magnesium, and silicon were observed here in Dubna, in the laboratory by Svetlana Pavlovna Tretyakova and her colleagues. As a matter of fact, the general case is such that the probability of decay, or decay time, depends on the probability of cluster formation on the surface of the nucleus, on the number of attempts to penetrate through the nucleus, this is nu, and on the permeability of the barrier for a given cluster. Here is what it looks like. If we take an alpha particle, the probability of its emission is, say, 1. Then, in order to emit silicon, it is 16 orders of magnitude less. But, nevertheless, it was experimentally observed, and this is a general law. The general law, which looks like this. Here is the emission time, and here is the mass. If we have alpha decay, say we take uranium-234, it emits an alpha particle, helium and thorium are formed. It can emit a cluster. It will form, say, this, and a neighbor, lead, will form. It can be divided into 2 parts, and there will be one here and one here. This is our world. There is penetration through the barrier. This is a process that will be extremely important for us, so that we may discuss the stability of these nuclei in relation to these types of decays. Weizsäcker's formula is brilliantly written specifically for the drop model. It contains the drop volume, surface tension, Coulomb repulsion inside the drop, an admixture of neutrons and protons in the drop, and finally, the pairing term. It is very small because, look here, here is this curve. This is an experiment. And the smooth curve is the calculation. This perfectly describes the binding energy of the nuclei. And finally, the last is fission. Fission was discovered by Hahn and Strassmann in Berlin in 1939. The correct explanation, from my point of view, was given by Lisa Meitner for this process. It seemed to me that this charming woman, completely forgotten in this era in fact, was the first to explain how fission occurs. While in Darmstadt, they named the elements that were discovered there, because they used cold fusion for this, which was done there. And I was invited there and was asked, what would you say if we give you the right to name one element, whatever you want? What would you call it? So I said Meitner after Lisa Meitner. This is how it came to be called Meitnerium, which they agreed with. We've gone through some history. In 1911, Rutherford said for the first time that there is a nucleus. In 1939, fission was discovered. Look, only 28 years later. And in 1942, the reactor was already working on the fission process. In 1954, the world's first nuclear power plant was used to provide electricity to a light bulb in Obninsk. And from 1955 to 2010, 450 nuclear reactors were built in 30 countries. 360 gigawatts of energy was generated by these reactors, which is approximately 17% of all the energy that humanity generates. 400 submarines were launched, and so on and so forth. This is all thanks to fission.